So today's topic is residue integration and residue theorem. Before that, we will go through some definitions which we have already defined. Well, now we'll more formally define this. So singularities and zeros. So what is a singularity? Okay. Now it is a point where f of z is not analytic or undefined. Okay, this is a singularity. Now, what is a zero? It is a point where f of z is equal to 0. So the point where the function value attains 0 is called as the 0 point. Remember, 0 is a point in the domain. It is the value of z. It is not the value of the function. So let's say at z equal to 2 plus 2i, function value becomes 0. Then 2 plus 2i will be called as 0. So okay, next there is another term called as isolated singularity. Isolated singularity. So by definition, this means that it is a point where the function is singular. However, in the neighborhood, there is no singularity. Okay, so if z equal to z naught, is a singular point, without further singularities in its neighborhood. In its neighborhood, okay, then it is called as isolated singularity. So many of the examples that we have taken is that of isolated singularities yesterday. Now, so we know that functions with isolated singularities, functions with isolated singularities have a Lorentz series expansion. Now, so if the principal part of the Lorentz series is of the form if the principal part of the Lorentz series is of the form B1 by Z minus Z naught plus B2 by Z minus Z naught whole square plus Bm by Z minus Z naught whole power m. That means, so that is finite number of terms. And the highest power in the denominator is m. Okay, for the principal part of the Lorentz series. Okay, then very important, Z equal to Z naught is called a pole of order m. Okay, pole of order m. So this is pole of order m. Z minus Z naught, the singular point, is also called as pole. Now, if m is equal to 1, that is only first order, that is only B1 by Z minus Z naught is the term in the principal part of the Lorentz series. Then Z equal to Z naught is called as a simple pole. So this is called as a simple pole. Now, if m goes to infinity, all right, that is the principal part has infinite terms. Then Z equal to Z naught is called an isolated essential singularity. That means you cannot remove this singularity at all. So by multiplying with any power, you cannot remove it as an essential singularity. Okay, so let's look at the examples. So the first one, f of z is equal to 1 upon z into z minus 2 whole power 5 plus 3 upon z minus 2 the whole square. Okay. Now we can further split this into partial fractions and see this. We can do this. So we can get 1 by z term and also 1 by z minus 2 plus 1 by z minus 2 square plus 1 by z minus 3 z minus 2 cube, like that. So highest power will be z minus 2 whole power 5. So here directly we can say, okay, f of z has a simple pole at z equal to 0 and a fifth order pole or a pole of order 5 at z equal to 2. Or pole of fifth order, like that. Now, next, f of z is e power 1 by z, which is 1 plus 1 by z plus 1 by 2 factorial z square plus 1 by 3 factorial z cube, so on goes up to infinity. Then we say f of z has an isolated essential singularity at z equal to 0. Okay. Now, similarly, we will do for zeros. F of z is equal to z square plus 4. Now we say f of z has two simple zeros at z equal to 2i and z equal to minus 2i. That means, see, we can factorize this as z minus 2i times z plus 2i. So each of them can be equated to 0. Now, power of each factor is 1. So therefore, it is a simple 0 because power of each factor is 1. Now, f of z is 1 minus z power 4 the whole square. Now this z power 4, see how we can simplify this. Let's look. This can be written as 1 minus z square into 1 plus z square whole square. Okay. Further, this will be 1 minus z into 1 plus z. This will be I. This will be z plus I, z minus I, whole power 2. So basically we get 1 minus z or z minus 1 whole square is the same, z plus 1 z plus I and z minus I whole squares. Now each of the factors can be equated to 0 and twice they give 0. There are two factors, right? So because we were able to write like this, we say that f of z has zeros of second order at z equal to plus or minus 1 and z equal to plus or minus I. Okay. So now we develop, so with this, now let's go further with this basic definition. Now we move to definition of residue integration method. So what is this residue? We have to explain residue integration method. So consider I is equal to closed contour integral over path C of f of z dz. Now we know that I is equal to 0 if f of z is analytic everywhere on and within C. Okay, by Cauchy's integral theorem, we know this. Okay, and now if f of z is of the form g of z by z minus z naught, okay, then okay, by Cauchy's integral formula we have I is integral of g of z by z minus z naught dz, which is what 2 pi I into g of z naught. 2 pi I into g of z naught. So these are both, you know, Cauchy's integral formula and Cauchy's integral theorem, the two results. Okay, where C is a closed path, a simple closed path enclosing z equal to 0, z equal to z naught. Now, so what the residue integral does, we'll discuss that now. So residue integration method allows integration of many forms of f of z along a simple closed path C. So now let us see how we can do that. So what is a residue? First we have to find out. So consider Lorentz series now. In the Lorentz series, of f of z about z equal to z naught, the coefficient of 1 by z minus z naught, or z minus z naught to the power minus 1 in the principal part of the Lorentz series is called as the residue of f of z at z equal to z naught. Okay, so yeah, so the coefficient of 1 by z minus z naught is b1, which is 1 over 2 pi I times integral, closed integral, f of z, which is if it has a pole, so yesterday we did this, just see, I will show the Lorentz series. Yeah. So this is B1. Bn is defined by this 1 by 2 pi integral closed over closed loop z minus z naught to the power n minus 1 times f of z dz. So B1, put n equal to 1, we'll simply get integral f of z, simply we get integral f of z. This term is 1. Suppose the second term, that means what will be the coefficient of what will be the coefficient of 1 by z minus z naught whole square. So you put that, you multiply z minus z naught to f of z and integrate. So this is from there we get this B1. So this B1, is called as the residue. This is equal to the residue of f of z at z naught. So we write like this: B1 is equal to residue we just write as res of f of z equal to z naught. Just like we write limit z equal to z naught equal to f of z. So the coefficient of the coefficient of 1 by z minus z naught in the Lorentz series expansion. So now you can see, so integral from here, we can see integral of f of z dz is 2 pi I times b1. So we can say that this is 2 pi I times residue of z equal to z naught of f of z. So integration can also be evaluated using residues. If we know how to find residues, that means we just do a Lorentz series expansion and immediately we can find the residue by the take the coefficient, and immediately we'll get the integral. So let us do an example. Yesterday we did integration using, Cauchy's integral theorem. We did so many problems. We did so many problems using Cauchy's integral theorem. Okay, 2 pi I into f of z naught. We did so many. Now we will use residue integration method to find this out. Okay. So now example 1. Evaluate closed contour integral of z power minus 4 sine z dz about a unit circle where C is a unit circle with center at origin. Now z power minus 4 times sine z is z power minus 4 times z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial and so on. This is 1 by z cube minus 1 by 6z plus z by 5 factorial 120. Okay. Minus z cube by 7 factorial and so on in finite terms. So now this is a Lorentz series. Okay. I want f of z. So if f of z is sine z, then integral closed loop about its pole is z equal to 0 is the pole of higher order, of course. This can be written as 2 pi I times residue of f of z at z equal to 0. Now what is, by definition, what is the residue? Residue is the coefficient of z power minus 1. So this term, the coefficient of this term is the residue. So we get minus 1 by 6 as the coefficient. So we get minus pi upon 3I as the answer. So this is the integral. So this one, apparently it is little difficult integral. Of course, you can do it using fourth derivative. We have done Cauchy's integral theorem for different domains. So we can use this formula that now f of z by z minus z naught whole power 4 will be third derivative of f of z naught, 2 pi I divided by 4 factorial. So we can use this Cauchy's integral theorem method. So if we want, we can do this. I'm doing this just to show that how lengthy it will be. Now f nth derivative of z naught is n factorial by 2 pi I times integral f of z by z minus z naught to power n plus 1 dz. Okay. So now this is sine z by z power 4. So let f of z be sine z and z naught is equal to 0. Then and for n equal to 3, you have to do. So third derivative at 0 is third derivative n is 3 factorial by 2 pi I integral of sine z by z power 4 dz. This is what we want. Now this integral is third derivative of sine. So integral sine z z power 4 dz over the closed contour including the pole will be 2 pi I by 3 factorial. This is what the answer. Now f of z is sine z, f dash z will be cos z, f double dash z will be minus sine z, f triple dash z will be minus cos z. So f triple dash 0 will be minus cos 0, which is minus 1. Okay. So here you get 2 pi I by 3 factorial times minus 1. 3 factorial is 6. So we get minus pi by 3i. Same answer. Same answer by using either Cauchy's integral formula or residue theorem. Advantage with residue theorem, we can see is so simple. 2 pi I times the residue, which is the coefficient of 1 by z term. So this expanding this is very simple. If we find the coefficient, 2 pi I times residue. immediately we can solve. So whenever we have this issue of, very high power in the denominator, um, the singularity of a very high order, then we can use residue theorem if we can. So the solution becomes very, very simple. Now, how to find residues in a simple way? Okay. Now, that we know how to find the residue, uh, how by residue integration method, it is very, very simple. So formulae to find residues. So the first one, or we'll write A, B, C, D. If f of z has only a simple pole, very simple. That means 1 by z minus z naught. Okay. So that coefficient, so residue at z equal to z naught f of z is b1, which is same as multiply the function f of z by z minus z naught and apply the limit z tending to z naught. What happens? Because this has only simple pole, you will get, say, b1 by z minus z naught term gets multiplied by z minus z naught, it cancels. And now all other terms will have factors of z minus z naught. So when we make limit z tending to z naught, you will get b1. So if you don't want to expand Lorentz series, we can do this. If we can expand Lorentz series, then it is easy. Now, next condition. Now let f of z be p of z by q of z have a simple pole at z equal to z naught. Okay. Suppose it has a simple pole at z equal to z naught. Then this denominator, suppose it is a big fraction, but it has a simple pole. The denominator can be written like this: z minus z naught times q dash of z naught. What did we do? I'm doing a Taylor series expansion of the denominator. Then z minus z naught by 2 factorial times q double dash z naught plus z minus z naught whole square by 3 factorial so on. What is happening? The first term will be z minus z naught, expanding Taylor series expansion about z equal to z naught. You will get q of z naught, which is 0, plus z minus z naught into q dash z naught plus z minus z naught whole square by 2 factorial into q double dash z naught, so on. So what I have done, we have removed z minus z naught term common. Okay. So now, um, now if we do, therefore, Z minus Z naught upon Q of Z will be 1 by Q dash Z naught plus Z minus Z naught by 2 factorial into Q double dash Z naught, Z minus Z naught the whole square by 3 factorial into Q triple dash Z naught, so on. Okay. So now, how do I find the residue? Residue is like this, no? So residue of Z equal to Z naught of f of Z from the previous result. It's a simple pole, but the function is like this. We have limit Z minus Z naught into Z minus Z naught times f of Z. So, which is limit Z tending to Z naught, Z minus Z naught into P of Z by Q of Z. Now, as Z tends to Z naught, P of Z becomes P of Z naught. Now, this one, you look at this, Z minus Z naught by Q of Z will be this expression. This expression, when you apply limit Z tending to Z naught, all these terms go to 0. So what we are left with? We are left with only Q dash Z naught. So this is the formula, residue of Z minus Z naught of f of Z, if it is in the form of P by Q and it is a first order pole only, is P of Z naught by Q dash Z naught. So this is the formula. Previous case, it was just limit Z tending to Z naught, Z minus Z naught times f of Z. Okay. Now suppose we have pole of any order, how do we find? Of course, best is if we can do Lorentz series expansion. Very easy to track it, but suppose it is difficult. Now, if f of Z has a pole of order m, so that means f of Z will have, the Taylor series part. We will have this Taylor series part plus now the Lorentz series part, B1 by Z minus Z naught plus B2 by Z minus Z naught whole square plus B3 by Z minus Z naught whole cube plus Bn by Z minus Z naught whole power n. Okay. Now multiply whole power m. Okay. This is order m. So of order m. So now let us multiply f of z by the highest power, z minus z naught whole power m. So each term of the Taylor series will be multiplied by z minus this factor, which means all the terms, the power of z minus z naught will increase. Now here we get b1 into z minus z naught to the power m minus 1 plus b2 z minus z naught to the power m minus 2, so on, plus bm. Okay. So now we want b1. So if now if this is z, if this is g, let us call this as g of z. Okay. So if g of z is given by this, then b1, yeah, b1 is this coefficient, right? So b1 is the coefficient of z minus 0 to the power m minus 1. Okay. And this, by definition, from the Lorentz series factors, okay, from the Lorentz series, this will be, what will be the coefficient? This now becomes the Taylor series expansion of bm. Then the next term will have z minus 0 whole power 1, next term z minus 0 whole power 2, so on. So each factor, now this factor will be, b1 will be factorial of m minus 1 in the denominator times the m minus first derivative of g. Okay, m minus first derivative of g. So that is b1. So we have converted this to a Taylor series and then did that. So residue of f of z now will be is equal to, in this particular case, pole of any or m, if the order is m, then we get this limit z tending to 0, limit z tending to 0, multiply this whole thing by z minus 0 whole power m. We need to differentiate it. So d, we are differentiating this. M minus first derivative z minus 0 whole power m times f of z. So m minus first derivative of g. So this is what it is. So this is the theorem. Again, as I said, as far as possible, expand the Lorentz series. It will make it very easy to find. So these are the ways to find residue. Okay. Now comes the important part of residue theorem, which is very, very useful for us. in solving problem. Residue integration method. Now we have residue theorem. Now residue theorem is used when there are many poles. Suppose we have a closed contour C. Now within that there are many poles or singular points. Now how to do this? Okay, how to integrate this in an easily manner. So let f of z be analytic. Inside and on a simple closed path C, except for finite number of singular points Z, I'll not say Z not, better to start with 1. So singular points Z1, Z2, Z3 up to Zk. Okay, then integral of closed contour of f of z dz is 2 pi I times sum of the residues of residues of f of z at z1, z2, zk. So sum of the residues, if we expand about different points. So integral, so residue theorem says f of z dz is 2 pi I. Suppose there is only one point, there will be one residue. Otherwise, it will be summation. Okay, summation of j equal to 1 to k residue z equal to zk of f of z. This is the residue theorem. So let us find. Okay. So let's do examples now. Now find the residues of f of z is equal to 9z plus I by z into z square plus 1. Okay. Now what are all the residues and evaluate integral f of z dz, where C is curve given by mod z equal to 2. Okay, so now f of z is equal to 9z plus I by z into z minus I into z plus I. So three simple poles. So f of z has three simple poles or first order singularities at z equal to 0, z equal to I, z equal to minus I. So how to find? Now, no need to do a Lorentz series expansion for this. Actually, we can either split into partial fractions. So if you split into partial fractions, we will get the coefficients of 1 by, see, we can write this. If we split into partial fractions, immediately we'll get that. So I'll write like this. We can split this into partial fractions of a by z plus b by z minus I plus c by z plus I and find ABC. So this is residue for z equal to 0. This is residue for B is residue for z equal to I when we expand about z equal to I, and C is the residue for z equal to minus I. Now, instead of doing the partial fractions, okay, we can find like this. Okay, residue for z equal to 0 of f of z is limit z tends to 0 multiply with z minus 0 9z plus I by z into z minus I into z plus I. This is very simple. 9z plus I by z minus I into z plus I. So we get 0 plus I by minus I into plus I. Minus I square is 1. So we get I. So this is the residue. Very simple. We don't have to do partial fractions. Now we can do residue of z equal to I. Residue at z equal to I of this function is limit z tending to I multiply with z minus I times the function. So 9z plus I over z into z minus I into z plus I. So of course, this cancels. I will directly write. I will not do one more term. Now, straight away apply the limit. You will get 9I plus I by I into I plus I. So we get 10I by 2I square. 2I square, I square is minus 1. So minus 5I. Next, residue at z equal to minus I is limit z tending to minus I, z plus I, it's 9z, the function, so this term cancels. Now this is equal to minus 9I plus I by minus I to minus I minus I. So this is minus 8I by 2I square. So we get I square will be minus 1. So we get 4I. So we got 3 residues we found for this. Okay. So now, where are these residues? Now, where are the points of singularities? Z equal to 0. Now, Z equal to I and Z equal to minus I. Okay, these are the 3 points. Now, where is the circle C? C is given by mod Z equal to 2. Mod Z equal to 2. Will be a circle like this. Sorry. Okay, approximately. So this is the path C, closed path C. Now this has 3. What are the 3 poles? Okay. This is 0, I, minus I, 3 poles. So when I have to find this integral, therefore, integral over C of f of z dz is 2 pi I times sum of the residues at 0, I minus I. So 2 pi I times at 0, it is I. Then at I, it is minus 5I. And at minus I, it is plus 4I. So this turns out to be 0. That is how we evaluate it using residue theorem. This is using residue theorem. Okay. This is a good example for practice. This is the easiest method for finding residues. Let us do another example. Okay, find the residue of f of z is equal to 50z by z plus 4 times z minus 1 the whole square at z equal to 1. Now we will have to use this formula. This is second order. This is second order. So we will have to either use this. I'll go by two methods. We will have to use this one because f of z has a second order singularity or a second order pole at z equal to 1. Therefore, residue of f of z at z equal to 1 is 1 by m. M is 2. 2 minus 1 factorial. Okay. Times limit z tending to 1 derivative of z minus 1 whole power m. M is 2 times f of z. So z minus 1 whole square. So we get 1 by 1 factorial only. Limit z tending to 1. Derivative of 50z by z plus 4. Okay. So this can be written as 50z plus 4 minus 4 by z plus 4. I will write this as 50 minus 4 by, no, 50 into 4 is 200 by z plus 4. So limit z tending to 1, derivative of 50 minus 200 by z plus 4. So differentiating, we get 0, then minus of 200 times minus z plus 4 the whole square, 1 by z plus 4 the whole square. That this will be the derivative. So we get 200 by 1 plus 4 the whole square, that is 5 square, 25. So we get 8. So the residue is 8. Now, where will we remember this formula? This formula may be very difficult to remember. An exam amidst so many formulas. But if you know the concept that residue is coefficient of, if it is at z equal to 1, it has to be coefficient of 1 by z minus 1. This is the residue. So what I'll do, alternative, you see this. This is an easier method. I'll write f of z. I'll split into partial fractions. It will be A by Z plus 4 plus B by Z minus 1, then CZ plus D by Z minus 1, the whole square. No. No, this will come when there's a quadratic term. So simple C by Z minus 1, the whole square. So equating the numerators now on both sides, we get A times Z minus 1, the whole square, plus B times Z plus 4 into Z minus 1, plus C times Z plus 4. So now we want any term. Suppose we want A. What do we want? By the way, we just want B. Okay, we simply want B. But anyway, B cannot be independently found because it has both the factors. Now put Z equal to minus 4. What happens? 50 into minus 4 is this term vanishes, this term vanishes. A times minus 4 minus 1, the whole square, which implies A will be minus 200 upon 25, which is minus 8. Okay. Now, next, see, this has linear term. This has coefficient, this has Z square term, this has Z square term. Left side equate. I want, my target is only one. I will not go find out all. My target is to find B because this is the residue for at Z equal to 1. This will be the residue. B is the residue. So equate coefficient of Z square. So 0 is A plus B. From there we get B is equal to minus A, which is 8. Therefore, residue of f of z, z equal to 1 is B, which is 8. This is easy. It's a coefficient of 1 upon z minus 1. So this is how we can find residue. Okay. Now let us do another problem. Evaluate cos z upon z dz, where C is a unit circle. When it is just mentioned unit circle, it means about the center origin. Center as origin. So two methods. Okay. One first method. Cauchy's integral formula. We did this. Now, pole or singularity z equal to 0 is 0 is the point of singularity. So basically we get integral cos z by z dz. F of z by z minus z naught is 2 pi I times f of z naught. So this is 2 pi I times cos of 0. Okay, z naught is 0. F is cos z. So you get 2 pi I. Simple. Method 2. This was an easy problem. Now, residue integration. Or residue theorem we will directly use. Now cos z upon z is 1 upon z by 1 minus z square by 2 factorial plus z power 4 by 4 factorial. This is cosine series. Okay. Now we get this is a having a simple pole at z equal to 0. So what is the residue here? Very clearly, residue of cos z upon z at z equal to 0 is coefficient of 1 over z, right? At z equal to coefficient of 1 over z, which is equal to 1. All right. So by residue integration method, integral 0 cos z by z is 2 pi I times sigma of all the residues. Now we have only one residue in the unit circle. So 2 pi I times 1, which is 2 pi I. So either we can use, just a second. Okay. Um, you all, I'll give you 2 minutes to solve this. Please attempt to solve this question. Okay. All right. So see this circle. First of all, let us draw the curve. This is 0. This is I. This is 2I. This is 3I. Now, the circle is such that the center is I and the radius is 2. So this will be the radius. And here it will pass through this point. So let us draw this circle. I may not be able to draw exactly. Okay, let's take this as the circle. Okay, this is the circle. This is C. Now, this is minus I and this is minus 2I. This is minus I and this is minus 2I. So now you see this one has only one pole. So f of z is 1 by z square plus 4, which is 1 by z minus 2I into z plus 2I. And in fact, straight away, we can write this into partial fractions. Z minus 2I plus by z minus z plus 2I. If you add, you will get I have to get 1, right? So I subtract and I do. When I subtract this, I'll get z plus 2I minus z plus 2I, that is 1 by 4I. So now the poles that I have here within the limit of integration, within this circle of integration, I have only this one. Okay, 2I. So z minus 2I. So this one. So I get residue of z equal to 2I of f of z is coefficient of this term, that is 1 by 4I. 1 by 4I is the coefficient. So therefore integral of f of z dz is 2 pi I times residue. So 2 pi I into 1 upon 4I, I and I cancels. Then we get pi upon 2. We get pi upon 2. This is the answer. So of course, with Cauchy's integral theorem also, we will also get the same thing. Okay, but this is one method to do that. Clear? So problems like these are common in GATE. Now evaluate. integral f of z dz, where f of z is 1 by z plus 2 whole square, z minus 2 whole square, and c is mod of z minus 2 equal to 2. So first thing to do, very first thing to do in this problem is identify which are the poles or which are the singularity points that lie within this path of integration. So first of all, draw the path of integration. Now this one, at z equal to 2, so z minus 2, mod of z minus 2 equal to 2 means center is at 2 and radius is 2. This is 0, this is minus 1, this is minus 2. Now this f of z has second order poles. Second order poles at 2 and minus 2. We have got second order poles at 2 and minus 2. Okay. So now for this path, see, we don't require minus 2. So we just need to find residue. Okay. If we just find the residue at residue of f at z equal to 2, because okay, I have to write this. F of z has second order poles at z equal to 2 and z equal to minus 2. But of this, we need to find residue at z equal to 2 only. How do we find? We can use, the integration, we can do this 1 by 2 minus 1 factorial. I'll do the other method also. Z tends to 2, z minus 2 the whole square into f of z. This is the easy method if we know the formula. So z minus 2 cancels, you get one by 2 plus 2 the whole square. That is 1 by 4 square, that is 16. Oh, I'm sorry. We have to do a derivative of this. I forgot. D by dz of z minus 2 the whole square. So we get limit z tends to 2 minus 2 by z minus z plus 2 the whole cube. So we get minus 2 by 4 cube So minus 2 by 64, you get minus 1 by 32. So this is the residue. Therefore, integral over C f of z dz is 2 pi I times the residue, two pi I into minus 1 by 32. So minus pi I by 16. We can do it by Cauchy's formula also. By first derivative, you get similar. More easier method is, I would suggest, do partial fractions. You'll not make a mistake in this. Now 1 by z minus 2 the whole square into z plus 2 the whole square. I'll write this as a by z minus 2 plus b by z minus 2 the whole square plus c by z plus 2 plus d by z plus 2 the whole square. What am I looking for? I am only looking for a, because I have to find only residue for at z equal to 2. That means I have to find coefficient of 1 by z minus 2. Coefficient of 1 by z minus 2. So I am looking for this term. I need to find a, that is the residue. So here residue of f of z, this is f of z, as z equal to 2 is a. Here I need to find a. So I can find a. 1 is a times z minus 2 into z plus 2 the whole square plus b times z plus 2 the whole square plus c times z plus 2 into z minus 2 the whole square plus d times z minus 2 the whole square. Okay. Easy way, put, I want a, our target is a. So put z equal to 2. So 1 is b times 2 plus 2, 4 square. All others are zeros. So b is 1 over 16. Now put z equal to minus 2. A term goes, B term goes, C term goes, D times minus 2 the whole square, which is D 1 by 16. Now B and D we have found out. If we can find either C or for that we will have to find C and A. So put z equal to 0. See what happens. 1 is 2, 4 into minus 2 minus 8 plus 16b plus 4 into 2, 8, 8c plus, no, sorry, this is 4b. 4b plus 4d. Now, so we get, let us do this, we get 1 minus 8a minus c. Now plus B and D are 1 by 16. So 1 by 4 plus 1 by 4. So we get A minus C as, this is minus 1 by 2, take to the other side. A minus C as 1 by 2 by minus 8. So minus 1 by 16. Now, now equate the coefficients of Z cube. Zero, A plus C, which means C is equal to minus A. So substitute this here. So you get A minus of minus A is equal to minus 1 by 16. So 2A is equal to minus 1 by 16. A will be minus 1 by 32. So we could find A from here, which is same as this residue. So A is the residue and it is minus 1 by 32. Therefore, integral two pi I times the residue. So 2 pi I times minus 1 by 32 is minus pi I by 16. All right, last problem. We'll stop with this. If we just do these problems that I'm doing in class, any problem you will be able to solve. Evaluate, find this I, Z power 4 minus 3Z square plus 6 upon Z plus I the whole cube dz, where C is a simple closed path enclosing Z equal to minus N. Either use Cauchy's method or this is pole of order 3. This is pole of order 3. So using residue integration, now residue of f Z equal to minus I is 1 by, this is m is 3. So 3 minus 1 factorial limit Z tending to minus I. The second derivative 3 minus 1 of Z plus I the whole cube, Z power 4 minus 3Z square plus 6 upon Z plus I the whole cube. So this and this cancels. So 1 by 2 factorial limit Z tending to minus I. First derivative is 4Z cube minus 6Z. The second derivative will be 12Z square minus 6. So 1 by 2 into 2I square minus 6. I square is minus 1. So minus 18 by 2 is minus 9. Therefore, now there's only one pole and encircling. So integral of this function is 2 pi I times minus 9. That is minus 18 pi I. So using residue integration, we can do like this. What if you don't remember this formula? Then simple alternative. Alternative is write z power 4 minus 3z square plus 6 by z plus I the whole cube as 1 by, oh, this is cube, this is power 4. So first of all, you have to do the division. This will be a little tedious task. First, we'll have to do a division. Let us see if I can do that. This is z times so we get z cube plus 3zi. We'll have to do a division. Plus I cube is minus I. So this will be z power 4 plus 3z square z power 4 plus 3z cube I minus 3z square minus I times z. So I have 3z square plus 6 I have available. So therefore z power 4 minus 3z square will be z into z plus I whole cube minus 3z cube minus z times I. So plus 6. Oh. Anyway, this will be a little lengthy division. I was trying to shortcut it. I'm not getting. So we will have to go by the integral. Okay, we'll use Cauchy's integral method. Here, splitting into partial fractions. If it was power 2, it would have been easy. The numerator is power 4 and this is denominator is power 3. So 2 terms you need to do. So let's see. This little difficult. It's not, if we spend time, we'll get it. Alternatively, we can do this as, write this as f of z by z plus I the whole cube using Cauchy's integral formula. What is that? F triple dash z naught, or f double dash z naught will be 2 factorial by 2 pi I times integral f of z by z minus z naught the whole cube. So 2 pi I by 2 factorial. So we get f of z by z plus I the whole cube dz is 2 pi I by 2 factorial times f double dash z naught is equal to minus I. So the same what we did, this is pi times I double derivative 4x cube 12 4z cube 12z square minus 6z, sorry, minus 6 z equal to minus I. So pi times I two by I by 2 factorial. Correct, n factorial by 2 pi I. Correct. I'm getting a difference of 2. It should not happen. I'm just saying pi times I. Okay. 12I square minus 6 get minus 18 pi I. Their answer we are getting as 9 pi. No, minus 18 pi I. Correct. Correct. Residue is 9. So minus 18 pi I. So this is using Cauchy's integral formula. This is using residue integration. Wherever possible, if Lorentz series term we can find the coefficient of 1 by z plus I. That way we'll be able to solve. Okay. So with this, we complete the complex analysis. Just what all did we cover? We covered complex functions. And on this complex functions, we get many problems, basic complex numbers. And this problem set that I discussed in detail, This is very important. We get many problems on this. Then we discussed complex differentiation. In this, very important is Cauchy-Riemann equation is the most important part. In if you just know this, mostly question comes on this analytic and Cauchy-Riemann equation. All others are simple. There's hardly anything in that. So Cauchy-Riemann equation problems. Okay, we did a few problems. Then complex integration. We discussed, integral over a closed path of two functions, one by z and one by z minus z naught. Then very important, very important is Cauchy's integral formula and integral theorem. So integration part is quite important, and Lorentz series and residue integration. So with this, we end complex analysis. So by next weekend, 2 classes are sufficient for me for numerical methods. So with that, we complete the syllabus, and then we will do some practice problems. So by next weekend, Saturday and Sunday, I will cover the syllabus. Okay, I end the class today here. I will share these notes.